And so in the context of working with these highly engineered polymer composites, we think about the idea of something that has lots of good properties. All right, so yeah, I did skip the wrong way. So thermoplastic additives, we have environmental resistance. We have to worry about the effects of heat. And so creep, which is something that in the context of inorganic materials, we typically don't have to worry about until 800, 900, 1,000 degrees centigrade. Polymers can creep at room temperature. Polyethylene is especially famous for that under certain biomedical circumstances. Light stabilizers, I talked about polypropylene before and how sunlight can affect it, and so we're looking at light stabilizers as being added to any type of polymer that's going to be outdoors, for example, because they know they need to worry about that. Flame retardants, especially for plastics in contact with electronic components. You don't want your keyboard catching fire when you spill Diet Coke on it, so they have flame retardants built into plastics, and as a consequence, we all carry some small amount of those flame retardants in our bodies right now. The livers of blue whales in the deep oceans have flame retardants in them because they've become so ubiquitous in terms of electronic materials, especially polymers. We also have, making things even more unavoidable, our processing additives. And so this has to do with how we make polymers. And so if we want to, you'll make the ballpoint pens you guys are using, they're injection molded and then have to be pushed out of the mold. And something that helps them come out of that mold are these lubricants that are built into the plastic composition itself. And so again, this is something that is everywhere all the time, all around us. Plasticizers, this is, again, one of the surprising things that are necessary for plastics is something that makes them less brittle. And so plasticizers are huge in the area of plastics. So PVC pipe, which most of us have seen, PVC pipe is 40% plasticizer. It's an enormous amount. It's almost more plasticizer than it is PVC. Okay, and so again, additives loom large in the area of plastics. And then if we have foaming agents like what we use to make styrofoam, for example, those involve certain types of foaming agents that are used as systems. All right, and so we talked about fillers, thermostats, and so forth. And these issues associated with polymers can sometimes lend themselves, and these are great examples of situations in which we need to have not just these issues associated with stealth, which involves the use of carbon fibers, so it doesn't reflect radar as easily, but then we also have a special matrix that goes around those carbon fibers that holds them together. It involves fabrication of the skunk works and McDonnell Douglas, very nasty things. And so we have a couple of situations in which these aircraft see very high stresses when they're banking at 9G, enormous stresses. And so those carbon fibers are there to provide the resistance to those stresses, and then there's a polymer matrix that goes around them that holds everything together. All right? These high temperature polymers I mentioned last time, polyamides especially, are used in this application. They're relatively brittle, and so one of the nasty things about these aircraft is that someone drops a wrench on the wing, then it shatters a small amount of that polyamide, and then the guy flying the plane says, oh, I got some black fuzz sticking out of my wing because that guy dropped a wrench on it, which means eventually they have to replace the whole section of that wing in order to deal with that black fuzz. But these are designed for these very high stress situations in which we need special, in this case, radar. And so this is an example of reinforcement, and we talked about fiberglass before. So it's everywhere, fiberglass, especially in boats and a lot of planes as well. Epoxies and thermosets in which we have a high temperature or a high rigidity matrix surrounding a fiber that is even higher modulus. And so we get this shared behavior involving this load transfer between these two phases that is used in both boats and cars. We also have examples of thermoplastics that are reinforced using similar techniques. There's a broad class of material called sheet molding compounds that are heavily utilized in the automotive industry. So you make a sheet, you polymerize it in place with some type of reinforcement, and then you take that sheet and you mold it into an automobile fender. All right, so it's a very common operation where you have many thin layers of sheet molding compounds that get molded into these automobile fenders. And so this is a big part of the area of polymer manufacturing. And you can go to a variety of companies, and this is just one example. Quantum Composites up in, is it Bay City? Yeah, Bay City, Michigan. So they make a lot of composites for a lot of different applications. And so this is a huge business. There's a whole world of composite manufacturing that involves this process of taking fibers and mixing them in using a process in which the fiber and the polymer matrix are pultruded is the word they use, but it's basically squishing the two together, getting the polymer phase to infiltrate into those fibers, either via compression or by just infiltration with the epoxy matrix, followed by polymerization. All right, and so there's a whole art form, a whole world of this process of composite fabrication that starts with a polymer matrix and then it achieves a certain type of reinforcement for these very specific types of goals in both aerospace and commercial applications. All right, so a very important area of plastics. Okay, so what led to all this? And what led to all this was the concept of polymer bonding. And so this is something that is important because it's relatively new. So we have thousands of years of metalworking history, stoneworking history, even glass. It's been around for a long time. About 100 years ago or so, actually, pretty much right around 100 years, people finally accepted the idea that you could have such a thing as long-chain polymeric matter. So not 1,000 years old, just 100 years old at most. And as you can see in this excerpt from a letter, dear colleague, leave the concept of large molecules well alone. There can be no such thing as a macromolecule. Basically said, you're crazy, you belong in a lunatic asylum because you think that long-chain matter exists. Okay, so that's how strong the pushback was to the idea of long-chain polymeric matter, that they were writing each other these very polite letters that weren't saying very polite things in the end. So this was fortunately overcome, and so these synthetic efforts, as we now know, ultimately became successful and proved the concept, and so all the doubters had to finally give up and essentially go off and die. And then we had this process of making a lot of different plastics that suddenly really took off and made the world as we know it, essentially. And so there's this issue as part of this process of chain length as a function of appearance. And so the simplest way to illustrate this is to talk about this progression. What is this compound? Methane. All right, so we have one carbon here. And if we go to, let's just say pentane, which is how many carbons? It's supposed to be 5. All right, so this is a gas, methane. We have 5 of them now. What's this? What's pentane? Huh? Liquid. Very good. All right. Butane, on the other hand, 1 carbon less than that, is a liquid, at least room temperature conditions. Inside the lighter, it shows up as a liquid because it's pressurized. All right, so it's just on the edge of being a liquid. And then we go to a little bit longer. Let's just say 20 carbons in the polymer chain, which is, I think it's called dodecane. And this is very definitely a solid. It's a waxy solid, all right, but we would still consider it a solid. And so this is all based on the fact that we have carbon and hydrogen, and we're just growing that chain length. Chemistry-wise, it's all carbon and hydrogen. All right, so there's no chemical explanation for this because those atoms still interact with each other in the same way. It's the concept of increasing chain molecular weight and the fact that we have those carbon-carbon bonds, which, as you know, are very strong bonds in the system. And that's what drives this process of translation solid. All right, and then we have other aspects that go into the design of these polymers, and I'll give you kind of an obscure example, which is helpful in terms of understanding what's going on in these systems, and that's if we have carbon double bonds in a polymer chain, and there has to be, oops, here we go again, there has to be 4 bonds per carbon. Now, it's one thing you guys should be aware of if you don't know it already. Every carbon has to have 4 bonds. All right, so if I ask you to draw things on a test and you have less than 4 bonds on each carbon, there's a problem. All right. And this is a compound that relatively famous. It's called polyacetylene. Meaning that it's derived from a polymerization of acetylene gas, very flammable material. So we polymerize this, it gives it this structure, and this is kind of interesting stuff because it allows for the flow of electrons under the right types of potential and doping along the polymer chain. So it holds out the possibility of having conductive plastics, which would be phenomenal in terms of weight advantages versus flying a ton of copper back and forth across the country in every 747. We instead have something that's conductive and is very low density, then that'd be great. Unfortunately, polyacetylene has a tendency to burst into flame when it's exposed to the air, so not so good in that aspect of things. There's other issues as well. But anyway, the thing about this stuff is that because it has those double bonds in the system, all right, those double bonds don't allow for rotation. All right, the regular polyethylene single bonds, it can rotate around those carbons. Those double bonds, there's no rotation allowed. And so this ends up being a relatively stiff material, all right, because those polymer chains can't rotate and translate and move very easily because of that inherent stiffness associated with them. Okay, and so the characteristic of those carbon-carbon bonds control the macroscopic properties. We also have, much closer to home, since we just talked about it, the case of, and let me make it easy to see, this particular polymer. That was an awful example of drawing capabilities there. Sorry. All right. What polymer is this? Polystyrene. Recycling number. Very good. All right. You're getting there. Okay. So we have this large group. We talked about this last time. All right. You have this shorthand. We make it look a lot smaller than it actually is, right? There's 6 carbons in that group. And in order for this rotation and translation to take place, these guys have to slide past each other. And as you might imagine, given the size of this side group, they're much better. All right. These guys tend to bang into each other. And so these polymer chains are trying to slide past their neighbors. Okay, so this doesn't exist in isolation by itself in space. These polymer chains are rotating, sliding past their neighbors. And this large phenyl group, or benzene ring, if you want to think about it that way, will bang into its neighbors and prevent that process from occurring very easily. So this is why, as I mentioned last time, polystyrene is considered, at least in its native form, relatively stiff and hard, because it's difficult for those polymer chains to slide past each other. PET, on the other hand, as I talked about, it has those ball bearings, makes the process much easier. That's why we don't make soft drink bottles out of polystyrene, because of this issue associated with the rotation of the polymer chains. All right, and then on the other hand, the other extreme, basically, we have these issues associated with the fact that we have situations in which the rotation is relatively easy. And this is a polymer that's called silicone. I'll come back to this probably. And this is one of the very few examples that you'll see in this class of a main chain that's not carbon-carbon. This is SiO, 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 Si. And so this allows, partly because we have these oxygens built into the chain, it allows for this process of easy rotation. So these guys can flip and rotate and translate, and so as the polymer chains move past each other, this is relatively easy to do. All right, don't have big bulky side groups getting in the way. We have the ball bearings in the chain. Everything is great in terms of flexibility. All right, so these are very important aspects, and the impact on properties. So, as we talked about before, we also have these outer chain effects between these chains, all of which, at least for the most part, are made up of carbon and carbon, and these fall into the category of van der Waals bonding. All right, van der Waals bonding is not just one thing. All right, hydrogen bonding is one example of van der Waals bonding. The way hydrogens interact with each other, which isn't necessarily hydrogen bonding, is another example of van der Waals bonding. It's a category, not a specific example. It includes all intermolecular forces. In terms of the source of this bonding, this gets into things that don't make a lot of sense coming from the primary chemical bond area. And that's when we have two hydrogens looking at each other, all right? Is there a reason for those to be attracted to each other in any way? What might cause that to happen? Anybody know? So we have carbon, huh?
Dipoles.
Dipoles, which are caused by, you're onto it. All right, so we know that the carbon-hydrogen bond is electronic. It's all electrons flowing back and forth between these really tiny nuclei on both ends. And so those electrons can shift back and forth. And as they shift back and forth, you see these distributions of positive and negative charge show up in these systems. And that's how polyethylene, which otherwise has no reason to hang together, that's why polyethylene exists as a solid, because there is some transient short-range attraction between those hydrogen atoms. And that's what holds them together. That's why polyethylene is not a liquid. Otherwise, if there was no bonding, it should be a liquid, right? And so we have these intermolecular forces. It's one of those days that are significant to us because it controls its ability for translation. To occur or not occur, as the case may be. All right, and so they have to be able to rotate, translate, slide past each other, and the amount of bonding between them determines how easily that is, how easily that process can take place. So I have polyethylene I just started talking about. I have PVC, we have chlorine. That chlorine sees a hydrogen atom on the neighboring polymer chain and hydrogen bonds to it. All right, so right away, this process of polymer translation is made more difficult in PVC because they have to slide past each other. And what happens here, and this is kind of a foreign concept, you have a secondary bond between the hydrogen and the chlorine, all right? That's the strongest van der Waals bond in existence, by the way, hydrogen bonding. And that bond, in order for the polymer chains to slide past each other, that bond has to break and then reform someplace else, all right? So we're breaking secondary bonds when the polymer chains slide past each other. We're not breaking primary chemical bonds. That doesn't happen here, okay? So make sure that you don't confuse those two. Secondary bonds, relatively weak, impermanent, they're flexible, they can form, break, and reform very easily. All right, and so this happens during this process of polymer translation. Any questions? Yes?
So the secondary bonds would be the side groups?
Secondary bonds form between side groups, yes, that's right. Any other questions? Does that make sense? And so as you can imagine, when you have these polymer chains sliding past each other, if I deform a polymer, I'm not driving dislocations with that polymer, I'm making those chains slide past each other. And so there's a lot of rotation and translation going on. They slide long distances past each other in order to deform that polymer in a visibly substantial way. All right, so this is something that happens a lot in terms of controlling properties in these systems. We also have other things going on, as if that wasn't enough complication. We have a polymer chain, and we have a different polymer chain, and these things were formed by polymerization. And the polymerization process isn't dictated. The chains just kind of propagate in whatever direction they want to. And so they can entangle, which I'm trying to draw here, but it's easier to visualize it between your fingers. Those polymer chains entangle, and if I try to strain that system, I have to strain that entanglement. All right, so this is a very powerful force, especially for things like polyethylene, and that those polymer chains can entangle. In order to slide them past each other, I might have to break the bond in order to make that process complete. And then in real systems, of course, things are nowhere near as simple as this. I can have one polymer chain, and then I have this neighboring polymer chain, and it can do all kinds of funky things. It can go in and out, back and forth, and go over here, for example. There's no rhyme or reason for it. It wasn't engineered to be a certain way. They just grew, and they ended up like this as a result of the polymerization process. And so obviously now, if I try to strain this system one way or another, put a stress on it, should I bend it or stretch it or what have you, then those entanglements will interact with each other. And especially as we get toward the end of the straining process, as we're trying to fail this polymer, so we might have like 1,000% strain on the system, that's when these entanglements really start to take hold and keep these polymers from failing. Okay, so it's not just about how the chains see each other, it's also what happens when they physically try to interact. Okay, any questions about that so far? All right, and so as we talked about so far, we have carbon-carbon bonds, and as you know, these are sp3 hybrid orbitals. The allowable angles in this system range from 105 to 113. Equilibrium is what? 109.5. All right, so they'd rather be 109.5 degrees. All right, but we have a little bit of a range. If I try to go to 114 degrees, what happens? Breaks. All right, the bond can't exist. sp3 hybridization won't allow it to exist beyond that angle. So we have a little bit of give, an 8-degree give in that system. And so that's what polyethylene has to work with in terms of trying to move chains past each other, that 8-degree give. And so, again, keep in mind we have the spaghetti representation of things, low resolution, but then we zoom in and we have that bond angle that we have to work with of 109.5. And so as these polymer chains have to slide past each other at the atomic scale, that issue of bond angle dominance is important in terms of allowing these chains to go past each other or not. And so it's a very complicated process of a lot of chain motion, kinking back and forth, trying to make use of that 8-degree give to allow the chains to go past each other. And so this is something that is a consequence of that type of bonding. Important, in the special case that I showed you a minute ago, but these siloxanes, or silicones, don't call them silicons, silicones is the correct word, we have, instead of an 8-degree give, we have a 76-degree give. All right, so what does that mean? It means that we have enhanced the ability for relative chain-chain motion in these systems, greatly enhanced. And so this is why we talk about silicone rubber. It's not that it's necessarily cross-linked, it just has this tremendous ability to give. All right, and that's one of the things that makes it rubbery, even if we don't have any cross-linking in that system. This has the lowest rotational energy of any commercial polymer. So again, we have these SiO, Si components of the main chain, and we have CH3s on the outside of that, on the silicones alone. And so the oxygens, as we saw for the case of PET, make everything even easier because they act as ball bearings, and the fact that these angles themselves can range over such wide ratios of bending means that it's easier for these chains to move past each other. There's another name for this, which is polydimethyl siloxane. PDMS is the official chemistry name for this, but we call them silicones largely. All right, so this is certainly very important as far as the properties are concerned. All right, and secondary bonding, of course, isn't necessarily limited to any given chain. We talk about going back and forth. We have bonding that happens between two different polymer chains, and so we can have something going on in between these. It can be dispersion force bonding, it can be hydrogen bonding. Those kinds of bonds, again, they form, break, reform as this process of sliding takes place. We can also have bonding within a given polymer. And really, when it comes down to it, this is probably the more important characteristic of polymer chains and how they control the behavior of a plastic, because a polymer chain is 100,000 units. All right, it's not stretched out. All right, it's definitely not stretched out. They're actually kind of a kidney shape in plastics. And so, for the most part, polymer chains are seeing themselves. They're not necessarily seeing their neighbors. The neighbors are important too, but a lot of what is controlling deformation is happening within individual polymer chains because they are so long. They occupy a lot of space. And so this process of trying to strain something and deform it in a certain way is going to put stress on those individual polymer chains, and they have to slide past themselves. All right, so keep that in mind. Interpolymer bonding is important, but also intrapolymer bonding is important as well. Any questions about that so far? All right. And then we get into some other aspects of this that will become important later on. And this first one is configuration, and this is something that's an order determined by the chemical bonds themselves. And so in this context, this has to do a lot with the type of bonding that exists between the carbons in these chains. And this configuration of a polymer cannot be altered unless chemical bonds are broken. And so this configuration in space is typically associated with more rigid polymers. And a good example is shown here, in which we can have, this could be, well, it's not polyacetylene, but you have something that has a double bond in the chain like polyacetylene. Right away we know it's a little more rigid than it could be if it was just polyethylene. And we have the arrangement in space of the carbon atoms going in and out of that double bond. And as you can see, they're different. All right, we have one, for those of you who are refugees from organic chemistry, cis and trans configurations for these systems. All right, and so in the case of this configuration, cis and trans, they can't alternate. They can't go back and forth. The double bond won't let them. All right, so that configuration, the arrangement of these atoms in space is fixed. Unless you break the chemical bonds, of course, then you can change things. And we can't undo this by rotation because, again, that double bond is there and prevents the process from rotation from happening. Okay, so that is also an example of issue of secondary bonding. And then we get into something that is, at least commercially, certainly more important. And we have this issue of configurations of polymer chains. And so we have different ways of achieving this. So if I have this polymer chain and I make all those blue atoms chlorine, what polymer do I have? PVC recycling number? No, not 6. 3. All right. Okay. Okay, and this is showing you those chlorine atoms, and it can be methyl groups or whatever. They're all on the same side. And the same side is referred to as isotactic arrangements in space. I can conversely have this arrangement going back and forth on opposite sides, and that's called syndiotactic. And so these are both possible depending on the chemistry of how we polymerize these things. But where it becomes interesting, both of those can crystallize if I have what's called atactic. That means we don't have either. All right, we have no dominance there. And so what this means is I can take atactic polypropylene, which is probably the most famous example. If I have isotactic polypropylene, I have crystallinity. If I have syndiotactic polypropylene, I have crystallinity because it's all the same. All the puzzle pieces are the same. If I have atactic polypropylene, it's amorphous. Very famous example. So atactic polypropylene gets used all over the place because of this fact that it has this amorphousness built into the structure because the polymer chains are arranged in space so that it makes the puzzle pieces not the same. All right. If it's isotactic, they're all the same. If atactic jumps back and forth, it's hard for it to crystallize. All right. So a simple way in which we use chemistry to control properties well downstream of that chemistry. Yes?
Would the entire chain be isotactic or just like sections of it?
It depends on what you want, but typically it's all isotactic. Yeah, the chemistry is usually dominant. Any other questions? All right, and then we have other issues associated with bonding, which we've kind of seen before. We have cross-linking, which in Goodyear's case involved a sulfur atom that caused bonds to form between polymer chains and gave us rubber. We also have molecular weight, which has to do with essentially how long the chain is, how many carbons are in that chain. That's a general question. And so we know that controls the physical transformations of the polymer from a gas to a liquid to a solid to a ultra-high molecular weight polyethylene, 1,000,000 units in the chain of ultra-high molecular weight polyethylene with these fantastic properties that make it useful for certain biomedical applications. But it's also important to realize that it's not ideal. All right, so an ideal polymer, they'd all be one chain length. And you can actually make these. You can make plastics that have one chain length, expensive as heck. You get very slight improvements, so nobody does that. The real polymer molecular weights, so what's shown here is a narrow molecular weight, whoops, come on, a narrow molecular weight distribution, but in reality, it's more typical that they have what's shown in red, which is broad. All right, and so when you think about polymer molecular weight, if I go buy a jug of benzene, you know, all those benzene molecules have the same molecular weight. If I have polyethylene, almost none of them have the same molecular weight. There's a huge range of molecular weights associated with systems, and so it's not a defined compound in that sense. And it's the same chemistry, but the lengths of chains are all over the place. And so we can control this to control the properties in a variety of different ways. And so these are important. And in many cases, it's important to find out what went wrong. So things happen, plastic behaving like it's supposed to because it does weird things. We're supposed to get a nice Gaussian, all right? We're all used to thinking about Gaussians. In the real world, however, molecular weight doesn't pay any attention to what we like. And so we can have molecular weights that, in this context, as you can probably easily imagine, consist of a couple of Gaussians sort of mixed together. All right, and so this is typically indicative of a process that is somewhat out of control, and so we can have two different molecular weights mixed together, which give us a peak like this, and so it becomes difficult to say exactly what the molecular weight is. And what can be even worse, there's what's called the Tromsdorf effect, which is what happens during free radical polymerization, which is one of the reasons why PVC used to blow up, because this would happen during the synthesis of PVC, in which we have one curve, or one Gaussian, another Gaussian, and in between them is zero. All right? And so if we have in this case, number average molecular weight that is in between those peaks, we may have actually no polymers that have that particular molecular weight. But our characterization techniques, and we'll talk more about this later, say that that is the average molecular weight in between those two peaks. But again, none of the polymer chains in the system may actually have that molecular weight. So when things go horribly wrong, in this case, you're getting a lot of high molecular weight polymerization going on, you can have crazy stuff like this happen. All right, so your average molecular weight may be the same for two batches of plastic, but you can have entirely different mechanical behavior based on things like this going on inside the system. Okay, so molecular weight is broad, and molecular weight is, in many cases, very important in terms of controlling properties. And a single number value characterization of molecular weight can get you in trouble. And we'll talk more about how those are determined later on. But keep in mind that that is the way we think about polymers and their behavior is determined by molecular weight. But you see in the catalogs, which is what we do a lot of in the lab, unfortunately. Okay, any questions about that? Does that make sense? And it should make some sense if we try to explain some of these behaviors. If we have shorter polymer chains, are they going to move more easily or less easily than longer polymer chains? What? More easily. Okay, I thought I heard less. All right, so we have short chains. They're closer to being liquids, right? So they're easier to move around and so forth. And so it makes sense that if I have, for example, plastic that creeps too much, I might go in there and say, okay, do I have a low molecular weight species in there? That could be responsible for that creeping behavior that we see at room temperature in some of these systems. So that's a good example of where things can go wrong for us as far as controlling molecular weight. And then we also have another category to discuss, and that's conformation, which is the order that arises from the rotation of molecules around single bonds. Okay, and so rotation is possible in these single bonds, unlike a double bond, which I just got through showing you is impossible. You have to break the double bond to make it rotate. Rotation of an atom in this way relative to other atoms it joins is an adjustment of the torsional angle. And so this is an example of what that looks like from the standpoint of energy. And so if I have a polymer, and I guess in this case you can think of the red atoms as chlorine, all right, so this could be PVC, and the blue atoms are hydrogen. As we cause this rotation of one of those bonds around the other, so we're looking at, let's see if I can hit it right. So we'd have this peak, which amounts to a maximum in terms of the potential energy is associated with the situation in which these two chlorines actually rotate to see each other. Okay? And that should make sense. Chlorine atoms are electronegative. This gets back into this balance of charge issue. All right, so the chlorine is trying to pull electrons to itself. That's what gives it the properties that it has. And so those negatively charged chlorines are not going to like being near each other. There's a repulsion associated with it, even if they are separated by a couple of carbon atoms. And so there's a repulsion to that process that causes this to have these higher energy values when that particular torsional angle is achieved. So these conformations can control the energy of the polymer chain, which can in turn control the properties of the polymer chain and the plastic itself. All right, and so conformations are very important to us. In plastics, I guess in biology they're even more important. We have three-dimensional conformations of proteins and so forth that make proteins actually active. Otherwise it's just a stupid polymer without any biological activity. It has to have a certain conformation to be active, and that's part of this process of rotation. Any questions about that? All right, and then last but certainly not least is where we start to try to intersect with what everyone is used to thinking about in terms of microstructure. Okay, so a lot of what we talked about so far is carbons bonded to carbons, maybe bonded to hydrogens or chlorines, a couple of angstroms in length, 1.5 angstroms or so. Very, very small things. So we used to think about microstructure, we think about a big hunk of steel or aluminum or something that with these enormous grains. And we think about controlling grain size, very important in terms of the properties of the metal especially, and then properties of ceramics as well. And that's a key aspect of working with inorganic materials, is how do we modify grain size? You guys have heard about that. We have grain size modifiers and so forth that can keep grains from growing, and that's a huge deal. In the case of polymers, not so much. It's what I've told you so far, which is secondary bonding between polymer chains at the 1 to 2 to 3 angstrom range. That's where the majority of the physical control of these systems exists. All right, so that's why you'll never see someone talking about changing the size of the crystallinity in a polymer, because we don't normally worry about that in polymers. The other aspect of this is that we have differences in size. Polymer microstructure is 10 to the 4th larger in magnitude than any of the previous factors, and so we do have microstructure, and this is an example of that for nylon 6,6, a very popular form of nylon. And you're seeing these structures, these alternating dark and light structures, and this is called the Maltese cross pattern. And it's completely an optical illusion. There are no regions of dark or light polymer in this system. So we're taking plane polarized light, passing it through the polymer, and that plane polarized light is preferentially eliminated in one direction and then accentuated in another direction. And so those dark and light patterns show up, and they're not real. If I take the polymer and I rotate it, those multi-crosses will stay exactly where they are. All right? So they stay rigid, even though everything else is rotating. So we know it's an optical illusion, essentially. But it's also a very great way of saying, oh, crystallinity is present when we see these things. And then we have another polymer, of even greater interest, polyvinylidene difluoride, which does have some electrical properties. It's been used for a lot of sensors under stresses and so forth. And this is an example of something that looks very highly crystalline. There are no grains in this picture. They look like grains. There are no grains anywhere in this picture. So when you talk about plastics, never ever use the word grains. It makes no sense. All right, what we're looking at, even though it has a lot of familiarity to us in terms of that structure, what we're actually looking at are objects called spherulites. And a spherulite is a three-dimensional object, just like a grain is a three-dimensional object, except that it's not a single crystal. It's made up of many small crystals, all of which have nucleated and grown out of a single site. Whoops. Am I going to lose you? All right, they've nucleated and grown out of a single point, and they continue to grow, and within those individual lamella, which is the word we use to describe polymer crystals, we have the situation in which these polymer chains are sitting inside that crystalline structure, but then outside of this, it's all amorphous. So we have amorphous polymer chains in between this. We have amorphous polymer chains sitting on top of the crystalline areas themselves, but we don't have a grain anywhere in this image. So when I look at this other structure, this is this difference in order of magnitude that becomes so important. You know, I look at this and I say, "Huh, that's perfect. There's no amorphous stuff anywhere in there. Actually, it's riddled with amorphous content." All right, because what you're seeing are these optical illusions, these Maltese cross patterns that show up when we have these spherulites present because of the interaction of light and these individual lamella. But the reality of it is, this could be 50% crystalline and 50% amorphous. Okay. So it looks like grains. There's a nucleation and growth process. They impinge on each other. They look like grains, forming grain boundaries, but there aren't any grains anywhere in that image. All right? And the other aspect of this relates back to something I said earlier, and that when I talk about a polymer chain, remember the polymer chain was there first, and it was formed by these random polymerization processes that just let them go wherever they want. So I can have a polymer chain that just kind of wanders around and goes in and out of all these different spherulites, and ends up over there, for example. All right, and so this is totally counter to what we think about when we think about grains and grain boundaries, especially. So grain boundary is a region of what? Anybody remember? First off, is there anything in a grain boundary? Anybody want to guess? All right, so we think of grain boundaries as a bunch of Shockley disorders, Shockley dislocations, right? A mesh of Shockley dislocations. We think of it as a region of local atomic disorder. We think of it as transition between two different orientations of crystalline matter, right? So there's arguably nothing there in a grain boundary, right? Because it doesn't really connect very well. In this context, we have these polymer chains. They were there first. They go in and out of these spherulite boundaries. They go in between these regions of crystalline amorphous component, so I can have that same polymer chain sticking with this color that goes in here, becomes crystalline for a while, then wanders around in between this and goes into there, and wanders around this crystalline material, then goes in the amorphous, and so forth, and then goes off into infinity. All right. So this issue of disorder and this absence of bonding between grains doesn't exist in these plastic systems, right, because the chains were there first. Okay? Any questions about that? Just think about it for a while, let it sink in. Fortunately, you guys haven't had decades of thinking about grains to unlearn, so this should be relatively easy. Okay, so I'll see you guys on Wednesday. And I'll start posting the recorded lectures now that they've been converted to YouTube videos. So you'll start seeing those. Has everyone accessed the Carmen site yet? Yeah? Okay. Good.